Good afternoon, everybody.
Good afternoon, sir.
Do you have any question, guys? Any doubts from last class? Okay. So I'm going to post the homework for chapter 2. Okay. So I'm into it, and this will be conducted on Moodle. Okay, so maybe I post tonight or by tomorrow, latest by tomorrow, and I will give you 2-3 days to solve it. Okay, so it will be some questions that you have to solve, maybe 10 to 20 questions, and the weightage will be 2% of the full grade. So 10 marks that we talked about for continuous evaluation. So out of that 10, 2 marks this homework will have. And this will relate to chapter 2. Okay. Also, everybody will get different question sets, you know. So please do your own work. Yeah. And the questions in mid-sem exam will be following the same pattern. Even for quiz will be the same pattern. Okay, so it's important to solve it yourself. That way you will learn it, and that way it will be easy for you basically later on. Okay. Okay. Now, so far we looked at two things, two methods. Okay, so we had two methods. Okay, so method number one, Kaledikin method. Okay, in which we had the strong form, and from that you found the weak form. And number two, we say Rees method. Yeah, in Rees method, you have the minimum potential energy formulation. Yeah, minimum potential energy formulation. Okay, and basically both you have seen that both are same. Regarding this method, we tried to solve a problem. Remember, there was some error. So remember that I also posted. So although I correctly wrote this formula, a cube minus b cube equal to a minus b a square plus ab plus b square. So I wrote the formula correct, but while really implementing it, I used minus instead of plus here. Because of that, we got the error. So you can replace yourself. You can put minus there, and then you see whether you get the correct answer or not. Did anybody do it?
Yes, sir.
Yes, sir. I got correct answer.
Yes, sir. Same with me.
I'm
Yeah.
Shubhanath.
Okay. Great. Okay. So basically, both are the same. They will lead to the same thing basically. Yeah, not very different. Now, just for the sake of completing, so we can check whether both are same or not. So one is first is the Garikin method. When used, we have converted the strong form to weak form. What about the weak form to a strong form? Can we do it the other way? So you know that we have, for any problem, for this problem, we can take any problem. For this problem, what we studied, we wrote like d over dx ea du over dx, right, plus bx is equal to 0, and subject to you had u x equal to 0, yeah, and then you have EA du over dx at x equal to L equal to 0. Yeah, so this is for this problem. So even if you can think for one problem whether it holds, you can write also general purpose, because you have got two. Basically general purpose writing will be a bit difficult, because you have two kinds of boundary conditions. You have to take some combination of that. So we can just take one example and you can show how we got it. We got basically we did a weight function and you integrated it. This is how you did in order to find out, right? So b dx L you did and you made equal to 0. Yeah, and then finally what you got was like this. We got w, right? Then ea du over dx, and you get L0 minus 0 to L ea dw over dx du over dx right, plus bw dx equal to 0 to 0. So this is what we called the weak formulation, right? Now if let us say if you are given this is the weak formulation that you are given, and can you get the same thing? Well, what you can do is from here you can go like you have the, so let's say we start from the weak, and from that too we have to go to the strong formulation. So we can start w d w ea du over dx, right, and you have L 0 minus 0 to L ea du over dx dw over dx plus bw dx 0 to L equal to 0. Now what we are going to do, we will do the integration by parts of this one, the way we did earlier. The same thing we can do, and what will we get? The same thing, exactly same thing. If you do integration by part, it will look like this: WEA du over dx minus, then you will have EA du over dx w, right? This you will get L to 0, then you will get minus you will get 0 to L w d over dx w du over d, sorry, ea we get here dx, right? Okay, and then we get plus 0 to L bw dx equal to 0. What we did, integration by parts. This one we wrote like this, integration by parts. Okay, so finally what we will get, you can see that this and this will cancel out. So of course we have L to 0 here. This and this will cancel out. This minus minus becomes plus, and you will have W this plus this. Yeah, so what you get basically is equal to 0 to L W, yeah, and then d over dx ea du over dx, right, plus bx, yeah, then dx equal to 0. So you got that, but still this is still in the form of the the weak formulation, because you have also integral, still this has the integral, right? So we have to take it out. Now this is true for an arbitrary w, or any w, basically we are talking about, right? So choose w equal to w naught, and exactly the same thing. It's up to you. You can take any form, any equation you can choose for w, right? So you can choose like w equal to w naught and d over dx ea du over dx plus bx. You can choose that, right? And then if you put it here, then what do you get? You get like this: 0 to L w naught and d over dx ea du over dx, right? Plus bx, a square of that dx equal to. If that is the case, you have w naught here, which is anything. I mean, again, w naught is arbitrary. Yeah, it could be non-zero value. It's arbitrary. And then you have this whole square. It's possible only when, so w naught is let us say w naught greater than 0 always. Since since w naught is arbitrary, we can choose any value. So that really means that the whole thing has to vanish. Otherwise, it will not be equal to 0. Yeah, so hence this has to be equal to 0. That really means d over dx ea du over dx plus bx has to be equal to 0. And this is what is the strong form. Yeah.
Pardon, sir.
Yes.
Actually, sir, without choosing sir W0, W0 this turn, we can directly say that W is the arbitrary. That's why sir dx ea. We can say that this one is 0. So
Sure,
we
sure. You
okay,
can
okay.
also do
Thank you.
that. You can also do that. Yeah,
Thank you, sir.
sure. Any other question, guys?
Sir, the boundary conditions, like uh, like from the weak form, uh, like strong form had different boundary conditions, right?
Strong forms, no, they have the same boundary conditions. The equations that you give are the same. Boundary conditions are same. Only thing, the solution you get will not basically the actually it will translate into the physical. It will not have the correct physical meaning. Equation wise, this will, okay, what I mean to say, let us say you have two kinds of solution, right? So one is a strong form. So a strong formulation, if you have solution, we have seen this goes something like this. Yeah, the same problem we are talking about. And what we see in this case that u0 equal to 0, du over dx equal to 0. This is coming from the strong formulation. Now, if you look at the, let us say linear, we have assumed a linear solution, and your solution is this line. Okay, now what happens here? We have in the equation for the weak formulation, we did put value in that equation. We did put du over dx value of that there. Yeah, but the thing is, actually it is not it is just turning into a constant. Basically, information is not there where we are enforcing it to be slope of that. So du over dx, we just convert it into a constant. Okay, what I mean to say is, see here, we have the, look at the weak formulation. And what do you have? You have W du over dx EA, right? You have L0, and then you have 0 to L, then you have EA dw over dx du over dx, and plus bw dx 0 to L is equal to 0. What happens? Here we put this one, we are putting some values here, right? So in that case, we put du over dx. So if you expand that, so we get w, sorry, w at L EA du over dx at x equal to L minus w at 0 EA du over dx x equal to 0. What happens here is this du over dx at x equal to L, we are removing it, means we are making this a constant, right? So whatever value we get, in our case, this value is 0, so we are just converting that equal to 0. This is 0 anyway because u is equal to 0, right? So what we did, we have entirely deleted this portion actually, or converted this, we are converting into a constant basically. So this u and this u are not the same. They are not the same.
So
Once
that's
you
why I'm asking, like when we matlab later when you had done integration by parts on it, in that time we had cancelled it, right?
at that time we cancelled it. Yeah, cancelled it, yes. Value wise, it will be the same, no? The numerical value, no, you are not getting one thing, is the numerical value will be the same in the both the cases. Only thing is the u here and u in the strong form, both will be different. Yeah? Did you get it or not?
No, sir, I'm confused.
Yeah, okay. So, okay. So let me write
Numerical
differently.
value as in,
Yeah, say again.
so like you said numerical value will be same. So like after putting to 0 and
Okay.
L or when.
Yeah, okay. Let me, I have not probably here. Okay. Let us see here. What happens here if you look at this point, what is the value of du over dx? This is the approximate solution you get.
So you're saying that at 2 points they both are having the same way. Okay, acha, okay, I got it.
Got it?
At two places they are having the same value. Okay. Okay. But the
Yeah,
function is not same. Okay, sir.
right. So that's the, I mean, this is the approximate solution, so if you say du over dx
So it
term,
be a different like a constant or something else if it's u.
right, yeah, you are taking this as a different thing, it is not enforcing there. Remember when we have this, we do not have a boundary condition. We don't write in addition to that du over dx equal to this. We don't write it because that's already incorporated here. But in the strong form, we have to write it additionally that this is what it is. That is the difference. Here already the boundary conditions are already, we already write within it. Because of that, what happens is whatever the solution we get, and what we solution, this will be a kind of equation you have. You follow?
Yes, sir. Yes.
Yeah. So if you write like this, what I mean to say is if you write like a weak formulation like this one, on top of that, we are not writing du over dx at this equal to 0. We are not writing that. So this becomes a single equation and we try to solve it. So that is the thing.
And sir, our W0 is 0. here, right?
Yeah, W0 is 0, yes.
Okay.
Yeah. So those things, when we do, it is easy to, solve it. But when you get the solution is not necessarily the exact solution. Yeah. So that's the problem. Any other question, guys? Okay. Similarly, we can the potential energy formulation we can have from the minimum potential energy, or you call functional जो formulation, we can convert that into the weak form. It's also possible. Yeah. Okay, and we know that we have the potential energy, we call it pi, and this U is given by, we had half EA du over dx square dx, and if you look at this, we have let's B here, bx, and here if we have f naught at the end, so we had in our formulation bx ux dx 0 to L minus f naught u at x equal to L, right? And we said that this is the one that has to be minimized, right? Okay, so that actually, yeah, Subnath.
Sir, can I, sir, actually, sir, in the potential energy statement, sir, you are using F0 as a term of the boundary, sorry, at the boundary force, means at a point force, but in the W0, in the sorry, this previous method, we did not use any kind of F0. Sir, why, sir, it is doing such like this?
No, I did not get you. Say again.
Sir, in the potential energy statement, sir, you are using, sir, F0, F0 UL as the additional force, sir. But, sir, in the last one, means in the previous weak form, you didn't use in the Galerkin method, you didn't use F0 UL. Why, sir? It is? Can you please explain, sir?
So no, you tell me where should that appear in the weak formulation?
Means in the Galerkin method, there is no F0 term, sir.
No,
In
so
the
that's why. So why do you think it should be there? So you just tell me first, okay?
okay, sorry.
Not sorry. I mean, I'm asking you. The confusion should be coming from somewhere, no? So why
Yes,
do
sir.
you think it should be there?
Because in the Galerkin method, there is also a boundary force present. It can be a boundary force present, but
How?
so it is a condition, because in the potential energy statement, if there is a boundary force, there is a body force and as well as boundary force. So in the Galerkin method, there must be, if this is the same condition both the cases, so there should be a F0 term also in the Galerkin method also,
Okay.
I think.
Yeah, sure. It should be there. It is there. You know. Only thing is
Okay.
problem is different. In earlier
Okay.
problem, if not, we do not put any force there. We solve just with this one. Here, when we use the potential energy, then we have applied a force, this force also. So you can apply that force here, and you can find out that you will get the F naught value there also. How you get F naught value? You see, you have here, if you
Yes, sir.
expand that, what happens? W dx EA. Here it is L, right? Here
Yes,
you
sir.
will have L minus W0. So when EA du over dx is nothing but F naught, you get WL multiplied by F naught.
Yes, sir. Now got it. Got it, sir. Clear, sir.
Got it? So
Yeah,
if you
clear, sir. So,
expand it, in earlier method, what we have where we put a value equal to, you see here. Why? Because there is no force applied. If there is no force applied, then we wrote like this: EA du over dx x equal to L is equal to 0. If there was a force applied here, we will write here F naught. If this is F naught, we can put here F naught then. It all depends on what kind of problem you are solving.
yes, sir. Thank you, sir.
Okay. Okay. So we see this thing here. Okay. Now what? We want to uh, make or convert that into a weak form. And how do you do that? So this is minimum potential energy. This minimum potential energy is already if U is a solution, then variation in any potential energy has to be equal to 0. How? Let us say you are going to change from U to U plus delta U. Let's call it is equal to U plus zeta W. Yeah. So that really means Ux plus zeta Wx, where zeta is a small. Okay, so zeta is very small. Wx is an arbitrary function, which could be something like U itself. Yeah. Okay. So zeta is very small, and so you are giving a small,
Sir,
variation. Yes.
sir, are we assuming this that ux will be a function of wx? Del ux will be a function of wx.
We are assuming arbitrary, no? Anywhere, if you want to check whether changing U is going to change the function, what will you do? You can arbitrarily add something little bit, a small. So del U is not U. You are adding some, like x plus dx, you write, right? So this is like a dx. But here we have, you are changing the displacement just a little bit. Very del U is very small. Del U we can also write in terms of a function Wx, which is arbitrary, multiplied by zeta. Zeta is very small. So this and this are basically the same, right? Yeah.
And these functions are as you are saying that they are arbitrary,
Hmm.
so they can be cubic or matlab, uh, any sort.
Any sort, yes. As long as it is finite, basically, what we want it to
Sir,
be, it has to be finite. Yeah.
sir, that's why I'm asking. Like, how can then we say it's finite? Like, yeah,
This is bounded. I mean, it will have some definite value, no? So unless it will have definite value, then it has no meaning. Then you are going to give infinite. Let us say if it is infinite, then what happens? Uh, Zeta multiplied by some infinite term is a small, that will also make it infinite. In that case, you cannot analyze it, right? For any analysis, what you want to do, it is something like this. If you know that you have, let us say this is U and this one is your pi, what happens, what we are trying to do, the solution, the pi U will be here if U is the solution, right? U is the solution, or you can say, so you can say U here, let's say U not call it, or U dash you call it. If U dash is the solution, then what will you do? If you want to check, we can take, see the value, what is the value here, right? So here it will be U dash plus del U. We want to find out what is the value here. Value here will be pi, here it will be pi u dash plus del u. Value here will be what? Pi u dash. What we want to do? We want to make del pi equal to 0, right? Why? Because if it is a slope here, if you see here, if slope is 0, so little bit here you go, you will be on the same pi basically. That's what we want to check. Del pi equal to 0 we will do. So that what we want to do is pi u dash plus delta u minus pi u dash is equal to 0 you want to make. Why? Because slope is 0. The slope is such that if you magnify, slope is something like this here. So even if you change a bit, you get the same here. It is a stationary point, right? And hence this is what we are going to analyze. U has to be, del u has to be very, very small. Tell that this is very small, or since in your weak formulation there is an arbitrary function there, so we have to introduce some arbitrary function. Otherwise, how will we make it equivalent? Yeah.
Sir, how are we fixing the domain? Like the range, how are we fixing that? Matlab, it can have any value, then it has like an infinite place.
Yeah, so that's why here Wx is finite, right? When you say finite means what?
Yes, sir. Yes, sir. That
Wx within the domain has to
less
be
than infinity.
has to be less than, has to be finite, because you
Yes,
can
sir.
say that this is integrable. You can also dx is finite, right? You got
Yes.
it? Or you also call it integrable, right?
Yes, sir.
This is integrable only when this is within the limit, right? It's not infinity. Otherwise, you can, I mean, this has to be integrable, right? So,
Okay, sir. Okay, sir. Fine.
okay. Yeah.
Sir, just can I put in?
Yeah.
Can be understood in such a way that with two endpoints or two boundary points, we are assuming an arbitrary function. The function is defined because of the endpoints, within the endpoints. That's why it is finite.
But it can run in between, ऐसे तो.
Hi, it is fine.
Yes, sir.
As long as it's integrable, it's okay, no?
Yes, sir. Within the limits.
Hmm.
Okay, sir.
If it's integrable, it's fine, no? You got it? It's not possible that this is infinite in between, and you get the finite value. Is it possible?
No, sir.
No.
Sir, and can we have like a rough edge also in between, like two different functions over different domains within 0
Yeah,
to.
it could be discontinuous, right? It could be from here to here, could be here to here, goes possible. This
Okay.
discontinuity
Jumps are possible then. Okay.
jumping possible. With all possibilities are there. Yeah. As far as W is concerned, but what happens is when in the weak formulation, however, we look at dw over dx term will be there. So in that case, there will be a problem here. So there is also something called differentiability. Yeah, so it also has differentiability. There is certain a smoothness is required. Yeah. So this is not a smooth. This is C minus 1 smoothness. There is the function, in fact, any function, this trial function, if you see continuity, if the x, either it can be like this, right? Or you call it C0 continuity, right? But what happens is if you differentiate, this becomes, it will be something like this. It will be like here, here, here. So not as smooth, right? This type of thing where they are not connected, like here you go jumping like this one, call it C minus 1 continuity. Yeah, they are, see here you cannot find the derivative here. Yeah, so this is not a smooth. Yeah, and so on. So if you look at when we solve, then what happens in the weak formulation? Weak formulation, we have something like this: EA du over dx, dw over dx, dx. Means what? If you look at here, if du over dx does not exist or infinite, can you integrate it? You cannot integrate it. So in fact, requirement of u and w are the same. And that is how you look at it. So in fact, wx or ux both has to be smooth enough, or also you also call kinematically admissible. You call it admissible. That really means it has the required smoothness. And when you say required smoothness, that means it has the derivative. It has the, so it is for example, if it is within, it can have a like as long as like you can have something like this. From here to here, let us say you have like this. Then or you can have like this. So this is the linear, what you call it, right? Linear independent function. This could be quadratic or cubic also possible, and so on. But when we have something else, something like within the domain, if you are going up and down like this within the same element, then it's not possible, because here you will have the different means the derivative is not defined. You got it?
Yes, sir. And in strong form, we'll need a higher level of
Right.
smoothness.
Sure. In a strong form, you get one step higher, means one order up you need.
Okay, sir.
Yeah. So all those things are just looking at the equation. You can find out what should be the nature of those tile functions. Okay. Now, guys, remember that we are not going too much into mathematics. Okay, this is by design basically. Okay, so we will look at from engineering point of view, and we will look at the physics more than mathematics basically. So although it is taught differently, in an undergraduate level we never go so much in depth, so much of mathematics basically. So we don't get into variational calculus and all. So even in your book, if you see, variational calculus is not there actually. Yeah. But still, we want to give the interface, basically, how they are connected, how the mathematical, what is the mathematical meaning of this. Okay, so coming back, we have u, we said u plus del u, and then we wrote it as ux plus zeta wx, where zeta is very, very small. Why we want to do? We want to find out del pi then, okay? Del pi will be del equal to pi u plus zeta w minus pi u, right? That will be equal to 0, as I explained earlier. This one we want to do. Yeah, and that means what? That really means first we can find out pi u plus zeta w is equal to half 0 to L EA, right, d over dx square will be u plus zeta w, the square of that dx. Yeah. Let's write all together. That will be easy. We can go do in one go. Yeah. So okay. So equal to, let's say equal to like this. Yeah. So 0 equal to this minus this equal to this is equal to minus okay minus we have the forces, so let's write forces here. 0 to L B u dx minus f naught times ul, right? But we have u plus so u plus zeta w dx minus u, right, minus u l, right, plus zeta wl, okay, multiplied by, this is u multiplied by f naught, okay. Then this is what we have about this one, right? Then we have to subtract half 0 to L EA du over dx square dx, right? Minus becomes plus now, so it will be 0 to L B u dx, and then you have plus again ul f naught, right? Okay, difference is equal to we can expand, so half 0 to L, and then you have EA, right? And then what you have is du over dx plus zeta dw over dx, right? A square of that, okay? Here only we can have minus du over dx square coming from, so what we are doing is this guy, this one and this one we are combining, okay? So we putting this minus this, okay, so that we can subtract nicely this term and this term we are taking first. So this is what we have. Similarly, we also take the other similarly, so 0 to L, then we have B, and you have U plus zeta W minus U dx. Yeah, and then you have plus minus only, and then you have last this term, this minus this term, okay. So you get just this one basically, but we will write it let's write it minus zeta wl f naught, so minus zeta wl f naught. Yeah, any question guys so far? Is equal to 0 to L EA, and here this minus this plus this, we can write like that, or we can also square it, and then we can do it. So if you square it, then what happens? If you square it like this, then this square plus zeta square dw So you will have like this. So we can write it here: du over dx square plus 2 zeta dw over dx zeta dw over dx square, right? Minus, you have minus du over dx square, right? So you have dx minus 0 to L. If you see u cancels out, so you get b zeta w dx, right? Minus you have zeta w L f naught is equal to, we can write the final form. Now look at here. You have du over dx square term, this we cancel out. So we cancel out this and this, and this is very, very small, this term, because zeta is very small. We know that together zeta multiplied by this is very, very small, right? So this is how they do analysis, that del u, this is nothing but del u. By design, this is our choice, that del u is very, very small, because we give some perturbation and see it's very, very small. So because of that, this will also be 0. So what we have is 2 zeta dw over dx, or multiplied by sorry, we will have dw over dx as well here, so we missed that. So we have both, so du over dx and dw over dx both. Yeah, so du over dx comes from here, dw over dx comes from here, so both are together. So what we see here, this 2 and 2 cancels out, so we get 0 to L. Let me use different color probably. Okay, so 0 to L EA du over dx, right? dw over dx.
So beta was also there. Eta.
Yes, yeah. Zeta is also there.
Yes, sir.
Yeah. Okay. So we have this. Then we have minus. Okay. Minus 0 to L zeta bw dx minus zeta wl w at L, right? F naught. Yeah, so finally we can write, we can have zeta in common, and we will have 0 to L, right? And then we have w EA dw over dx du over dx, and then you have a minus, so minus 0 to L B, right? W dx. Then you have minus zeta is outside, then WL, and then you have F naught is equal to 0. Now, if you take F naught 0 as the n force 0, this term will not be there, and what you end up with the same term as the one we worked on. Now remember that zeta is a small but is not equal to 0. A small but not equal to 0, right? Okay, so that means what? That means this thing has to be equal to 0. So we have 0 to L EA dw over dx du over dx minus 0 to L B wx dx minus WL F naught is equal to 0, which is the also you call the weak formulation. It's the same thing. What we got that time was minus here, then plus here and plus here, right? Here, but equal to 0, so it's the same thing. Any question, guys? Any confusion here? Yeah, okay. So here just to complete it, giving a little bit of rigor as far as the mathematics is concerned. However, all these things are not needed, at least in this course, because this is introductory course, and which is a first course basically. We are offering, it's a common between UG and PG. However, when students are purely undergrads, you teach it differently. When you have a purely postgraduate, then you teach it differently. But since we have mix, we want to mix a bit basically. Yeah. So this is how it is. The finite element analysis actually was developed by those working in mechanics, and mechanics is quite a mix of physics and mathematics, and hence this course is taught by various departments, those departments which deal with mechanics, like mechanical engineering, civil engineering, or it is also by mathematics department, for example, or even by physics department. So it depends. Like this is the course which can be taught by almost all engineering departments and science departments. Uh, However, the way it is taught will be different. Yeah. So from mechanical engineering, we will give more of physics perspective, the heat transfer perspective. We will know what equation we are writing, whether this is the elasticity problem or heat equation or diffusion with advection, all kinds we can see. In mathematics, you apply the equation, you write the equation, but physical significance may or may not be known. Here, when we write, we will write, okay, this is convective heat transfer term is coming. So this is conductive heat transfer, it is here, like this. It is advection term in diffusion. We will look at all these equations, so we have the elasticity, 1D elasticity. We will also look at the diffusion problem. We will also look at the heat transfer problem, and all will look like the same. Boundary conditions will be different. Symbols we will use different. Otherwise, it will have the same meaning. Mathematically, all will be the same. And we solve in the same manner. Okay, any question, guys? Okay. So as I told earlier, I will be posting the homework today or by tonight, by tomorrow. Okay. So I will give you 2-3 days. So solve it. It will be 2% marks basically. Yeah. So don't look at the marks just looking at, oh, just two marks. So not important. The thing is, if you solve it yourself, you will learn and it will help you in a quiz and midterm exam. Okay, so because pattern will be same, it will be Moodle based. I have already enrolled you guys on Moodle. Okay, so I will send you the information. Once it is complete, I will tell you it is up there, and you can start solving. Yeah. Any question, guys? Okay. If not, then thank you very much. I will see you guys on Wednesday for the tutorial.
Hello.
Yeah.
Good afternoon.
Yeah, good afternoon.
The homework.
No,
Will be from the
your
chapter
voice
2
is
or
breaking.
from
I
the
could not
recent chapter
hear.
you are teaching,
So chapter 2 only.
or the recent chapter.
Chapter 2 only.
Okay.
Chapter
Okay.
2 only, I told.
Okay. Okay,
Yeah?
sir. Thank you very much.
Okay.
Okay,
Yeah,
sir.
okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.